Test of goodness of fit. Among the several uses of chi-square distribution, one of them is goodness of fit test. As initially we started by hypothesis testing related to one standard deviation, where the one population standard deviation can be tested with the help of chi-square distribution. Another use of chi-square distribution described in these lectures were test of independence of two qualitative factors. Third use of chi-square distribution is the test of goodness of fit. And the last one among the list of four is testing multiple proportions. These are the different uses of chi-square distribution. And today in this presentation, we are going to highlight the test of goodness of fit. Test of goodness of fit check whether the two distributions, one of them is the observed distribution and the other of them is the uh, suggested distribution. These two distributions are uh, close to each other or not. So this is the way of testing the fitting of a distribution. Testing whether the observed frequency distribution follows a specific model. Observed distribution means uh, suppose a data is given to you in the form of a frequency table. The two columns should be there. One of them is a variable x, and we need one quantitative variable for this analysis. And the frequencies are also be given there. This distribution is known as observed frequency distribution. This distribution is obtained through the random sampling. And these frequencies are referred to as observed frequencies. And we proposed a model for this probability, this frequency distribution. The proposed model is referred to as theoretical model. Like we are assuming that this observed frequency table fulfills or follow a binomial distribution. The binomial distribution is a hypothetical distribution or a suggested distribution, which we are going to fit for this data. And the goodness is to be checked. Goodness means what? Goodness means whether this data is actually follow the binomial distribution or not. So the proposed model, one thing is the proposed model. So we should have a proposed model and observed model. Two things we have: proposed model proposed model may be the binomial, maybe the normal, or many other model we have that we may propose for this observed frequency distribution. So this is called observed frequency distribution, and this is known as a proposed model. We have to first fit the proposed model to the data, and after fitting the data, we have to check whether the fitting is suitable for the data or not, or this proposed model is suitable for this data or not. So this is to be tested by the goodness of it. So we have to calculate the probabilities first, probabilities through the proposed model. So we have to calculate the probabilities from the proposed model. After computing the probabilities, we have to find out the expected frequencies. Expected frequencies can be obtained by sum of all frequencies multiplied by the probability. Sum of all probabilities, sorry, sum of all frequencies can be represented by capital X. So this is capital N, sorry, not capital X, capital N. This is your total sample size, the total N, sum of all frequencies. So this table is to be constructed for a specified distribution for the fitting purpose. After computing the fitting of the model, we have to find out the value of chi-square distribution. What is the formula of chi-square distribution? So we have to fulfill f observed minus expected the whole square divided by expected. This is the formula for computing the chi-square goodness of it. The formula is exactly same as the formula of the test of independence, but instead of writing the O and E, I am just writing the FO and FE. So nothing is the difference in these two. The null hypothesis will be what? The null hypothesis will be the proposed model is good for the observed data. So the null hypothesis will be H naught proposed model is suitable for the given data for observed distribution against the alternate hypothesis H1 not good, fitting is not good, or the proposed model is not suitable for a given distribution. Suppose observed model is a binomial model and observations are given there. So we have to firstly the fit the model, and then the model testing is to be done. This is FO minus FE divided whole square divided by FE. The total is computed. This total is referred to as the chi-square observed value. So this is the procedure that we have to fulfill for test of goodness of fit. In the chi-square test of goodness of fit, the assumptions are what? Assumptions are, these are the three assumptions. All expected frequencies should be greater than 1. At most 20% of the expected frequencies are less than 5 allowed. These are the same assumption as the test of independence. The data must be a random sample. The only one difference is we have a variable and along with the frequency distribution. If we have the values of the variable, that we can construct the frequency distribution ourselves. The variable has a specified probability distribution, a specified distribution, or we can call it as a proposed distribution. The variable does not have a specified distribution. Alternate hypothesis formula is written in the same format as I used in the test of independence. Then finally, we have to construct a critical region, with the help of alpha and the degrees of freedom. Degrees of freedom for this distribution is n minus k minus 1. What is n? N is the total number of cells used in the computation of chi-square. K is the number of parameters estimated from the sample minus 1. This is the formula of computing the degrees of freedom. If all the parameters are given and none of the parameters are going to estimate through the sample, then the value of K will be 0 and general degree of freedom will be n minus 1 as it is given here. It is given here as C minus 1. C minus 1 will be used if the value of K is 0. C is the total number of cells used in the calculations. So this is very important. And if suppose I am fitting a binomial model for the specified distribution, then binomial has two parameters. One is n, other is p. If n is given in the problem and p is missing, the value of k will be 1 because p is to be estimated through the given observed distribution. Now we are going to complete 2 or 3 examples using the test of goodness of fit. Here we have to check whether the die is fair or not. The null hypothesis will be what? The die is fair. So we can have a null hypothesis, and the null hypothesis is die is fair. Along with the alternate hypothesis, the die is not fair, or the biased die we have. Die is biased, or the biased die with the H1. Biased die. Another way of writing this null hypothesis, as we can have the die is assumed to be fair. If we are tossing the coin die 60 times, then these frequencies will be approximately equal if the die is fair. If the die is disbalanced and unfair, then we may have a deviation among these frequencies. So another way of writing this H naught, we have observed model, and observed model is what? Uniform distribution. Data follows uniform distribution. Another way of writing this hypothesis is data follows uniform distribution. Is a discrete uniform distribution because if the die is fair, then these frequencies must be alike. And alternate hypothesis is data does not follow uniform distribution. So this is the null and alternate hypothesis. We have to find out the expected frequencies first. So as I told you, expected frequencies can be determined with the help of probabilities. So firstly, we have to find out the probabilities, Px. Px, by which distribution we have to obtain the probabilities? By uniform model. So we have to obtain the probabilities with the help of uniform model, means we have all probabilities constant. Then we have to calculate the expected frequencies. Expected frequencies can be obtained by n times Px. The 2 columns are needed. One is the Px and other is the n times Px. The next column will be the calculation of chi-square. I am showing all of these calculation in a Excel table. The 2 columns are taken from the presentation, and these 2 columns are shown here. In the column of X, we have the different values on the face of die and the observed frequencies. These frequencies are the observed frequencies. And what we are going to do here, we are going to fit a uniform probability model for the given observed distribution and test its goodness. So there are the 2 steps. One step is fitting of the model, And the second step is the testing of the model. The model is what? Model is the binomial model. So we have to first calculate the probability, sorry, not a binomial model, uniform model. So first you have to calculate the probabilities using mm, uniform model. According to the uniform model, all of these probabilities will be 1 by 6. So we have 1 by 6. All over there we have 1 by 6. So this 1 by 6 is to be copied to the all numbers. Mhm. It is not representing in the proper way, so I have to type it manually. 1 by 6, 1 by 6, 1 by 6, and 1 by 6. We have to write down 1 by 6 here with the, I'm starting it by apostrophe. The reason is these frequencies are, these probabilities are in ratio, not in fractions. So these are the probabilities, and after computing these probabilities, we have to multiply the probability with the total of n. Total can be computed by just auto sum function. The sum of the frequencies will be 60. So now we have to calculate the n times the probability, which is referred to as expected frequencies. So expected frequencies is equal to n times into px. So n is 60. So I'm just manually coding this formula here. 60 multiplied by probability. Probability is 1 by 6. So 60 into 1 by 6. This is the formula of computing the expected frequencies. And then the same numbers we have here, the total should be 60. So the total of expected frequency is 60 and the total of observed frequency is 50. So this is the observed frequency, and here we have expected frequency. In the next column, this process is known as the fitting of the distribution. Here at the moment, we have to check whether the assumptions of the uh, goodness of fit is fulfilled or not. All expected frequencies are greater than 1 and all expected frequencies are greater than 5. Therefore, the all assumptions of the goodness of fit test is fulfilled. Now, the next step is to calculate the values of chi-square. Value, the formula of computing the chi-square is chi-square is equal to summation observed frequency minus expected frequency whole square divided by expected frequency. Divided by expected frequency, and this frequency and that summation will be all over there. As I told you earlier, that the total will be on the ratio, not the total on the numerator only. So this formula can be computed with the help of Excel column. So we have here, we have to find out is equal to the bracket, observed frequency is 15, expected frequency is 10, and the whole square divided by the expected frequency is 10. So the first value of the chi-square is 2.5. And then I calculate all the values of the chi-square, and you can see the different values of the chi-square, and total of all of these will be 13.6. So this is the called FO minus FE, FO minus FE whole square divided by FE. This is the way of writing the formula, but summation will not be shown on the top because summation is basically the total of this column. So this is the value of chi-square statistics, and this value is known as observed value of chi-square statistics. So this is called chi-square observed. Chi-square observed is equal to 13.6. Now we have to construct a critical region, and critical region with the degrees of freedom chi-square 0.05, always right tail is to be used. Chi-square 0.05 with the degrees of freedom n minus k minus 1, and the value of k is 0 in this case because I have nothing estimated by the sample, and the cells are used in the calculation of chi-square. 1, 2, 3, 4, 5, 6 cells were used. The degrees of freedom is 5. This is 5 degree of freedom. This is not 0.05. This is 0.05. 0.05. 0.05. It is 0.05. Now we have to find out this value from the chi-square table. The chi-square 0.05 at 5 degrees of freedom, it is 11.007. So 11.07 is the value of the chi-square at 5 degrees of freedom. The value of chi-square is 0. The value of chi-square is 11.07. Chi-square critical value is 11.07 and chi-square observed value is 13.6. And observed value is larger than the critical number. So there is a null hypothesis is not true. The data provides sufficient evidence not to accept the null hypothesis. The alternate hypothesis will be assumed to be true. According to the alternate hypothesis, the data does not follow the uniform distribution. And we can say that the die is not fair. And obviously, we can see here the die is not fair because 6 is occurred 17 times, which is a higher deviation from 10. It is expected that 6 will appear 10 times, but actually the 6 appeared 17 times. 3 appeared 4 times, but it was expected that it should appear, if the die should fair, then the frequency of 3 should be 10, but the frequency of 3 in the observed data is 4. So there is a high deviation between the observed and the expected frequencies, then there is a possibility that the null hypothesis will be rejected. We can say that H naught is rejected, and we have null hypothesis is not true. This null hypothesis is not true. So we have rejected this null hypothesis and accepted the alternate hypothesis, meaning that the data is not fulfilling the uniform distribution. And other way of stating this hypothesis is the die is biased. Another example of goodness of fit is the data of playing cards we have. After repeating the experiment 64 times, the following outcomes were occurs. 3 cards are drawn from the ordinary deck. The total number of cards are 52, and 3 cards are drawn randomly from this DAC. The distribution is given here. So 21 times we have 0, 31 times 1, 12 times 2, and 0 times 3. What the Y is indicating, Y is the number of spades recorded. The 21 times no spade occurred in the 3 selected cards. 31 times 1 spade occurs, 12 times 2 spade occurs, and all the 3 spades did not occur anytime. So that, as we have selected the 3 cards randomly from the deck, therefore this distribution is referred to as observed model. And what is the proposed model? The proposed model in this problem is a binomial distribution. So we have to fit a binomial distribution on this observed model. How many parameters the binomial distribution has? Binomial distribution has 2 parameters. B for binomial, Y in this case, the variable is Y. And with the semicolon, we have to separate out the parameters. One parameter is N and other parameter is P. But in this problem, N is given, N is 3, because three cards are selected and we are interested to obtain the distribution of 3 spades in the selected cards. So N is 3, but the P is not given. P is we have to estimate the value of P with the help of this sample. So this sample will be used to estimate the value of P. The degree of freedom in this problem will be n minus k minus 1, and the k will be 1 if we are estimating the P by using the observed distribution. So I am completing these calculations in Microsoft Excel. We have a distribution. This distribution is to be fit a binomial distribution. And test its goodness. This is the problem. Binomial distribution is fitted. According to the formula, binomial distribution has 2 parameters. One is n, other is p. So n is given, n is 3, and p is to be estimated. So P can be estimated with the help of the observed mean, equating the observed mean with the proposed means. The observed mean can be computed by a group data fx. So we have f multiplied by x. This is the column which is required here. F multiplied by x. This will be 0, and this is to be computed for the remaining cells. And here I need the total of fx. So how the mean is computed? The mean can be computed with the help of group data. Group data summation mean, it is the observed mean, is equal to summation fx divided by summation f. Summation fx is 55 and summation x is the total of the column of f, and the total of the column of x can be computed here with the auto sum function. So it is 64. 64 times we have to divide it, 64. The answer will be is equal to 55 divided by 64. It is 0.5859. Now we have to equate the 2 means. Which 2 means? The observed mean and the expected means. Observed mean is represented by x bar, and the proposed mean, which is the proposed mean of the proposed model, by np. So now x bar is 0.8593 is equal to n. N is the number of spades, number of cards selected, and the p is unknown here. Now cross multiplying p is equal to 0.8593 divided by 3. This is the value of estimated value of p. So we can represent the estimated value of p as is equal to 0.893 divided by 3. P is 0.29, 0.297. Now what we have to do, we have to calculate the probabilities of binomial model with the help of P and N. So the value of P is B. Instead of X, we have, okay, X, I have write down X in the Excel. X with the semicolon, N is 3, and the value of P is 0.29767. We can use the exact value here. So we have to compute all probabilities with the help of these two values of N and P. So in Excel, I am going to compute the next column, and the next column is the probability column. Probability by binomial distribution. So we have to use the formula in binom dist. Binom dist is a binomial distribution. Return the individual terms binomial distribution probabilities. So we have to use this function, binom dist. It needs four parameters. One is the number s. It is basically the value of x for which we are computing the probabilities. Number of trials are 3, and the probability is 0.2976. Cumulative, if we need the cumulative probabilities, write down 1 here. If we need simple probabilities, the 0 should be there. So my first parameter is 0, probability of 0, and the value of trials. How many trials we have? 3 trials, because 3 spades are selected. The probability is 0.29767. This is the probability, and comma, true or false. If you need the cumulative probabilities, write true. If you need a simple mass function or the simple probabilities, use false. Close the bracket and press enter. This is the first probability computed by the binomial model, and this formula is to be calculated for the rest of the numbers. And the total of the probabilities will also be checked by autosum function. So we can see that exact total is 1, meaning that the probabilities are fine. In the next column, we have to calculate the expected frequencies. Expected frequencies, the formula is n times px. This is the formula for expected frequencies. So we can calculate the expected frequencies. N is 64 in this case. Whenever we are computing the expected frequencies, the total of f will be used. Whenever we are computing the binomial probabilities, n should be 3, because this 3 will be the last value of the column. Now, expected frequency, the first expected frequency is equal to the probability multiplied by, I'm using a constant number 64, because it is 64. The first expected frequency is 22, the second, third, fourth. These are the expected frequencies. All x1, 2, 3, 4. All expected frequencies are greater than 1, and one expected frequency is less than 5. So we can merge these two numbers. If we merge these two numbers, then there will be the less degrees of freedom for it, because this expected frequency is less than 5, and out of the 4 expected frequencies, one is less than 5, meaning that 25% expected frequencies are smaller than 5. So we have to recalculate the observed frequency and expected frequency here, because two cells are to be merged. The new expected frequency is FO. I am writing it as FO, and the next column is FE. So what are the FOs? 21, 31, and 12 plus 0. 12 plus 0 becomes 12. Now, in the same way, we have to write down the expected frequencies. I'm just rounding these expected frequencies: 22, 28, and 11.9 and 1.6 to be added. So this is 12, 12 plus 1, it is 13, 13.5. So I'm just computing it by 64 minus 22 minus 28, because the rest of the frequencies will be there. So it is approximately, it is 12, and approximately it is 2. To 12 plus 2 becomes 14. Total of the expected and observed will remain same. In the next column, we have to calculate the chi-square value. Chi-square can be calculated as FO minus FE whole square divided by FE. This is the formula of chi-square. So I'm computing the formula of chi-square. I'm just few adjustments, and these adjustments are just formatting, not adjustment. Now, it is equal to observed frequency with the bracket. Observed frequency is 21 minus expected frequency is 22, the whole square divided by the expected frequency is 22. This is the first value of chi-square, and then I have to calculate it for the remaining numbers, and total is to be calculated. Total of these three observations is 0.65. So I can say that the chi-square observed value, I'm just writing it here, chi-square observed value is 0.6525. Now we have to obtain a chi-square value at 0.05. 0.05 is a critical number at the degrees of freedom. Degrees of freedom will be what? Degrees of freedom will be mu n minus k minus 1. How many cells are used in the calculation of chi-square? 1, 2, 3 cells are used. So n is 3 here. And k is one parameter is estimated by sample, and minus 1. So this is equal to 3 minus 2. 3 minus 2 becomes 1. So the degrees of freedom will be 1. The chi-square with the 1 degree of freedom. So I'm taking the value of chi-square 1 degree of freedom from the chi-square table. It is 3.841. Now the value of chi-square observed and the chi-square critical, we both have values. The both values are, it is 3.1, 3.841, and this region is referred to as the critical region, and this number is in acceptance region. Data provides sufficient evidence to conclude that the binomial distribution is good for the given frequency distribution, and we can apply the binomial distribution on this data set. So I am concluding this presentation. In this presentation, I have covered the two cases. The first case is related to the goodness of fit test for a uniform distribution. In the second case, I have selected the binomial distribution to fit on an observed distribution. Whenever the expected frequencies we have, if the expected frequencies are not fulfilling the assumptions, so we have to merge the rows. So I have merged the two rows. These two rows in the expected frequencies are merged, and the merged frequency will be 14. If we merge the two expected frequencies, the corresponding observed frequencies will also be merged, and the total is there. The effect is what? The effect is, instead of four cells in the calculation of chi-square distribution, I have only three cells. That is one less than the actual number. The three is why we are using three here. Three is three cells are used here. It is not this three. The three, this is the three for binomial distribution. This is the n, but this is not the n which I used here. This n is indicating that how many cells we used here in the calculation of chi-square. So there is a confusion among these two n, but you should be clear. This n is the n of the binomial distribution, while this n in the degree of freedom is the number of cells here. Thank you very much for watching this video.